Hi, my name is Nuno Faria and I'll be presenting you the totally ordered prefix parallel snapshot isolation, or TOPSI for short. First, let's start with the problem that motivated this work. Developers ideally want a data layer that ensures transactional and strong consistency guarantees as a means to reduce implementation complexity. However, ensuring those guarantees in a distributed database system often has a negative impact on performance, and this is due to network latencies, to distributed coordination, to the fact that fault tolerance becomes the greatest challenge when strong guarantees are involved, and because metadata overhead increases storage and can make computation more complex. On the other hand, relying on weaker consistencies is not a viable solution for a large range of use cases, namely financial or retail. A popular isolation in centralized database systems is the snapshot isolation that achieves a reasonable trade-off between performance and strong guarantees. Briefly, transactions read from a snapshot of data from when they started, meaning provides non-blocking reads. However, snapshot isolation also presents performance challenges in a distributed setting, namely the fact that snapshots of different sites must all advance in the same order and at the same time, which raises problems of waiting for a snapshot to advance before being able to start the transaction. To solve these problems, different solutions have been proposed to extend snapshot isolation in order to make it more suitable for distributed systems. One of the solutions is the generalized snapshot isolation, that allows transactions to execute of an older snapshot. This in turn avoids waiting for the snapshot to stabilize in all sites before being able to start the transaction. However, transactions executing on older snapshots are more prone to abort, and additionally, a transaction might not be able to read its own immediate writes, which can be a deal breaker for some use cases. In this example, we have two sites. Site P executes transaction A, while site Q executes transactions B and C. Transaction A and B start in the same timestamp of 1. Since transaction A finishes first, it gets assigned a timestamp of 2. When transaction B finishes immediately after, it gets assigned a timestamp of 3. Since GSI does not wait, transaction C starts before site Q plus transaction A. This means that C will also have a start timestamp of 1, meaning it cannot read B's modifications. On commit, a conflict will be detected and C will abort. Another solution is the prefixed constant snapshot isolation, which extends GSI to ensure that a snapshot contains all locally commit transactions. In other words, the snapshot of some site might be old, but is guaranteed to have all transactions previously committed at that site. In theory, this reduces the abort probability and a transaction is able to read its immediate writes. However, response times are increased due to blocking before starting or finishing a transaction. Using the same example, transaction C will have to wait until all previous locally committed transactions are applied. This means that we will have to wait for transaction B to be applied, and since B cannot be applied after A, to ensure total order, C will have to wait for A as well. After that, C can execute with a starting timestamp of 3, meaning it will be able to read B's modifications and thus be able to commit. Despite both of these solutions being an improvement over snapshot isolation for distributed settings, they still present problems when it comes to abort probability or waiting for the snapshot to advance. To solve this, there is a parallel snapshot isolation, which allows different sites to apply transactions in different orders as long as causal dependencies are respected. This removes blocking, as there is no need to wait for remote transactions. A transaction can read its immediate writes, and reduces abort probability, especially in workloads that display locality access patterns, since a snapshot will evolve faster in relation to locally modified data. The main downside is that independently evolving snapshots might not be viable for some strict use cases. The main problem PSI faces is that common implementations are built on the assumption of data partitioning, either by sharding or by restricting object writes to a specific site. This causes different sites to end up with different views of the transaction history. The main problem with this is that they cannot be easily mapped to architectures that disaggregate execution from storage, which are growing popularity mainly in cloud computing environments. In addition, this also leads to a more complex timestamp management, which itself leads to a more complex snapshot materialization, conflict computation, and site connection and disconnection. These problems are exactly where TOPSI comes in. It ensures PSI, while at the same time guaranteeing that the history at different sites converges to the same totally ordered sequence of transactions. This property opens up the possibility of having multiple implementation options. For example, the data at different sites can be partitioned or partially replicated, completely replicated, or even shared among sites. Another property of TOPSI is that its optimal timestamp management yields low storage and computation overheads. Before diving into TOPSI in detail, I will first provide you a system model to better explain how it works. We consider that the system is comprised by 3 components: a generic key value store that processes all data and can be accessed by any site, a transaction oracle that certifies transactions and flushes data to the key value store, and a transaction middleware which is embedded at every site and is responsible for executing and applying local transactions. The transaction execution is as follows. A transaction executes at a site it started on. On commit, the site sends the transaction write set to the oracle. The oracle then certifies the transaction and, in case of commit, flushes the data to a key value store. It then notifies the transaction middleware of the result, which in turn applies it to its local cache in case of commit, forwarding the result to the client. Eventually, the other sites receive a notification when the transaction is flushed to the key value store. Now that we've established the system model, let us first see how TopSci handles time management. TopSci considers two different types of timestamps: global time, which is monotonically assigned to a transaction by transaction oracle when it commits, and local time, which is assigned by the transaction middleware to a local transaction when it is applied. The global time is mainly used for transaction certification, while the local time is used to compute snapshots. We combine these two timestamps to create a pair that is assigned to each transaction and their respective objects. Considering again the previous example, both transactions A and B have the start timestamp of 1.1. When A commits, it receives the commit timestamp of 2.2. The first 2 refers to the site increment's local time, while the second 2 represents the global commit order. When B commits, it receives the timestamp of 2.3. When C starts, it gets a signed timestamp of 2.1. This means it can immediately read locally commit transaction B and is able to commit. For executing transactions using TopSci, we have that for reading, we first look in the transaction zone's cache to see if the value was already overwritten. If not, we look in the site's cache for the most recent object that respects the following condition. The first part ensures that the transaction reads recent, locally committed transaction. The second part ensures that the transaction reads recent, globally committed transactions. If not found, we look in the key value store for the most recent record that respects the following condition. As for writing, the object's data, together with the current global time and the transaction snapshot of that specific key, is inserted in the transaction's cache. To certify a transaction, we compare, for each key in the write set, the respective global time that was read by transaction in its snapshot, with the most recent global time stored. If, for all keys, the most recent global time stored is less than or equal to the global time read by that transaction, it commits and gets assigned a new global time. Finally, to apply a transaction, the transaction middleware assigns the next local time and inserts the data to its local cache. Looking now at some preliminary results, we compare different solutions of PSI using TPC's image mark. As we can see, with a single site, all solutions display similar throughput and abort rate, meaning there is no significant difference among the 4 isolations in a centralized environment. However, increasing the number of sites to 4 yields very different results. As we can see, TopSci takes better advantage of using multiple sites, scaling almost linearly. On the other hand, both GSI and PCSI display similar results to the single site deployment. GSI, given it presents a significant abort rate, and PCSI due to the increased waiting times. Snapshot isolation, on the other hand, displays even worse performance than its single-site counterpart. To finish this work, we conclude that TopSci presents better scalability than GSI, PCSI, and snapshot isolation. The 2 timestamp solution used by TopSci ensures low storage and computation overheads, and the fact that different sites share the same transaction history means TopSci is better suitable to be applied in systems that disaggregate execution from storage. For future work, we envision the creation of an architecture built to TopSci that takes full advantage of parallelism in order to ensure the optimal performance. And with this, we conclude our presentation about TopSci, or totally ordered prefix parallel snapshot isolation. Thank you for your time.